It's my pleasure to welcome everyone for our special year seminar and to introduce Leonid Monin from EPFL, who will give a talk on discrete and continuous duality algebras.
Yes. Thank you very much for the invitation. I want to talk about some project which is partly progress, partly done. So I'll try to separate the progress parts with things which are still not 100% done. Okay, so I want to start with some classical construction of algebras with Poincare duality. So Poincare duality. So its construction starts with a pair of objects. One is a vector space V. And the other is a polynomial on this vector space. And maybe for today's talk, all my algebras will be over real numbers, but the construction is more general. But just for concreteness, let's take all the algebras and vector spaces over real numbers. So F is a polynomial, and moreover, it should be a homogeneous polynomial. So if you have such a couple, you can associate to it a commutative algebra, which maybe I'll denote A lower script f. And this commutative algebra is defined as the algebra of differential operators on our vector space V with constant coefficient quotient out by the ideal of annihilators of f. So maybe let me explain just a little bit better what is this differential operators and what's this annihilator. So if I choose an isomorphism, so let's say assuming so if this vector space V is finite dimensional, so it's isomorphic to R to the n, then we can choose a basis of this vector space, and the ring of the differential operators with constant coefficients will be just a polynomial ring in partial derivatives in our coordinate functions. And then the annihilator of a given polynomial is just the set of these differential operators such that if I apply them to f, then I get identically polynomial which is identically equal to 0. So it turns out that this set is an ideal inside of a polynomial ring. Since polynomial f was homogeneous, turns out that this ideal is also homogeneous. So this algebra AF, the first statement is that these algebras AF, they always graded. And moreover, they always satisfy Poincare duality. So really, it's graded with degrees from 0 to the degree of a polynomial f, which I will denote by d later. And the fact that they satisfy Poincare duality just means that there is a map from, first of all, that A0f is isomorphic to AD, f is isomorphic to R, so it has just the one-dimensional vector space, and also that the map from ith component times the d minus ith component of this algebra to the top degree component is a non-degenerate pair.
Does it work without assuming that V is finite dimensional?
V is finite dimensional? Yes. The construction works for infinite dimensional vector spaces as well.
Exactly the same. Like
Exactly the
F
same.
is like a
You
homogeneous
need to say
polynomial.
what do you mean by homogeneous polynomial? So homogeneous polynomial will be something which is restricted to any finite dimensional vector space as homogeneous polynomial.
Yeah.
But exactly the same construction works. It's
So I can imagine that F is like a homogeneous power series in infinite, probably many variables or something.
yes, yeah, but of like fixed degree.
Oh,
Yeah.
yeah, it's homogeneous, yeah.
Yeah. And actually, I'll mention one example of just that sense. Good later. So yeah, and there is one more property which is algebra always satisfies because we quotient in some polynomial ring by some ideal. So just by construction, this algebra will be always generated in degree 1. And there's a statement that says that there is certain universality of this construction. So any algebra A, which is graded satisfies Poincare duality, generated in degree 1. And satisfies Poincare duality comes from this construction. And I can tell you what we can take as a vector space and what we can take as a polynomial. And so as a vector space V, we can take any vector space which surjectively maps to A1. So let's say this is any vector space with surjective linear map. And then we map the polynomial f from V to R. So the way we define it is, okay, we have our map from V to A1. Then from A1, we can map to A to the D by taking an element of our algebra and erasing to this power, it's to the power D. And then we know that D-dimensional component is one-dimensional vector space. So maybe we want to fix this isomorphism in this algebra, and we call this isomorphism a degree map. This isomorphism is a top degree component of our algebra with one-dimensional vector field. So we apply the degree map. So, for example, the easiest situation is when we just take V equal to A1, and then our polynomial is taking an element and taking the degree of x to the top, degree of the x to the d. But more generally, you can actually take any vector space which surjects on degree 1 component. Okay. So of course you can ask a more detailed questions. So you can ask for your algebra to satisfy some more intricate algebraic conditions and what properties of the polynomial f you should ask for it. And this, for example, the Lorentzian property of polynomial f that tells you about some Hodge-Riemann relations in 1. But today in my talk, I will mostly focus with easier question, with a zeroth question, and all of this, which are probability and some analogs of this. I will not talk too much about this. Okay. So maybe let me give you one example how this construction gives you a description of some cohomology rings of varieties or Chow rings of Chow rings, sometimes of algebraic varieties. Because for us, the main example of Poincare duality algebras come from cohomology rings. And indeed, this construction can give you, in certain cases, description for this cohomology rings. So maybe as one of the applications of this construction, we can get description showering of smooth complete toric varieties. So maybe let me very briefly remind how this goes. So first of all, if you have a smooth complete toric variety, then right. So there is a correspondence between those divisors on a smooth complete toric variety X sigma. Maybe I should say ample divisors. They correspond to polytopes delta such that their normal fan is equal to fan sigma, which defines our toric variety X. So in fact, since I don't work, maybe I want to work with complete varieties, but not necessarily projective, and I might not have any ample divisors on my toric varieties at all, I should say that this correspondence can be extended. So actually, there is a geometric presentation for any divisor on X. So any divisor on X sigma, this corresponds to something which is called virtual polytope. And there are several ways how you can think about virtual polytopes, but there are quite geometric presentations of these objects. So maybe let me remind you how this construction works for in ample case, and maybe I'll just say a couple of words how it can be extended for non-ample case. So for ample case, the way we define the polytope is the following. So the polytope is defined by explicit inequalities. Any divisor D is linearly equivalent to the linear combination of toric invariant divisors. So these are T invariant divisors, which are parametrized by the rays of our fan. So now if we have some linear combination like this, we can define a polytope by explicit inequalities. So then for divisor, which is given as linear combination of toric invariant ones, we define a polytope delta H by taking all the points in this character lattice of our toric variety such that the inner product between X and primitive ray generators EIs are less or equal than HIs, which are our coefficients here. And these vectors EIs, these are primitive generators of rays. So maybe let me draw a picture which illustrates this. If we have our fan being just a fan of P2, so this is our sigma, then we have two boundary divisors, one which corresponds to the first ray, another which corresponds to this ray, third one which corresponds to the third ray. We can take a linear combination of A D1 plus B D2 plus C D3. And then this corresponds to a polytope where we take vectors X such that if you take inner product, so this primitive ray generators of these rays they're given by vectors 1, 0, 0, 1, and minus 1, minus 1. And you can write inequalities. So you want vector x, y, inner product with vector 1, 0 being less or equal than a. So which tells you that the first coordinate should be less or equal than a. Similarly, you want you will get that y should be less or equal than b. And lastly, you will get that minus x minus y should be less or equal than c. And this defines you a triangle. So these inequalities define you a triangle with a normal fan if you have certain inequalities between numbers a, b, and c. So what you obtain is your polytope will be this. If there is certain inequality satisfied between number a and b, c, you will actually have a non-trivial intersection between these hyperplanes, and you will get some geometric object. So this will correspond to ample divisors on the So maybe just in 2 words, if you don't have ample divisor, you can still define the hyperplanes. Hyperplanes where your inner product with primitive ray generators is hi's, and these hyperplanes where they will cut your character lattice space into regions, and then a virtual polytope will be some linear combination of these bounded regions. So it will not be anymore just a polytope, it will be some linear combination of polytopes. But what works well here is that no matter if we work in ample situation or this more general situation where we take all the divisors, we can talk about the volume of these polytopes. So if we have just usual polytope, we take normal volume. But if we get a virtual polytope, we take a linear combination of volumes of these bounded regions, and it's still a geometric object, which is well-defined geometric object. And there's a theorem which connects this volume of this polytope with the degree of a divisor on a toric variety. So this theorem is a version of Bernstein-Kosterenko theorem. Which says that if we take a divisor D, H, which is a linear combination of boundary divisors, and if we want to raise it, take its degree of this divisor, well, then this will be exactly the same as d factorial times the volume of delta H, where this delta H is a possibly virtual polytope which we associate to this divisor. And as a corollary of this theorem, and this algebraic construction, which I was telling earlier, we obtain the description for Chow ring of toric varieties, so of smooth complete varieties at least, which says that if you want to, you can describe the smooth complete toric varieties Chow ring as a ring of differential operators on this space of polytopes, virtual polytopes of a given normal fan, where you portion it out by the annihilator of a volume on this space. So this P sigma is the space of all possible polytopes of a given normal fan, and this is the space which describes divisors on our variety. So this is the space which has surjection to A upper 1. And it turns out that toric varieties, the Chow ring is generated in degree 1. So we're in a situation which described by this algebraic construction we discussed before. And the only thing which is left is to compute this degree polynomial, and degree polynomial coincides with some volume polynomial of the polytope. So we get this description. Okay. maybe let me just mention a couple more things that, of course, as an example, I gave a description for toric varieties, but similar construction works. Construction gives a Chow-ring of full flag varieties, or more generally, you can take the homogeneous spaces G mod B, whereas G is any reductive group and P is a Borel. And even more generally, you can do spherical varieties. Smooth, complete spherical varieties, which have with H star generated in degree 1. So this was observed by Kaveh, and basically he realized that a lot of degrees you can again compute as a under the assumption that so degrees of a divisors on spherical varieties can be realized as volumes of some polytopes, and then under the assumption that A star is generated in degree 1, they always have Poincare, so under the assumption that A star is generated by degree 1, you can run the similar description for their Chow rings, which are the same as cohomology rings in this case.
So the volume polynomial in that setup is actually the volume polynomial of some set of polytopes.
Yes. So, for example, for full flags, what happens is your Poincare group is the character lattice of the Borel. So for each element in the dominant weight cone, you have a polytope, which is called Guilfand settling polytope, which depends on the weight. And then the volume of the divisor corresponding to this weight is the volume of this polytope.
This has the special property that
it's linear.
Yeah,
Yes.
the sum of
Yes.
the polytope is
Yes.
the polytope of the sum.
Yes.
It's very special for spherical, right?
It's very special for spherical varieties, exactly, yeah.
Is there a degeneration to a toric variety?
Yes, there is, yeah.
Already in the full generality.
Yes, in full generality as well, yeah. Okay. And okay, so this gives some presentation for Chow ring, but also you can study it a little bit more. And I don't really have much time to talk about this, but for full flags, in the later work of I think this so in the later work of Kirichenko, Smirnov, and Monin, they studied the case of full flags GLN mod Borel a bit more, and they realized they identified Schubert classes of Schubert cycles inside of the cohomology ring in the language of polytope combinatorics of Guilfand settling polytopes. So they said somehow how to write the classes of Schubert varieties in terms of the certain phases of the Guilfand settling polytope. So they were able to do some calculations with these classes for corresponding phases. You can use this description to get some more geometric view on some of the section. Okay, so this all was kind of an introduction. So let me now move on and tell about slight generalizations of the whole picture. The first question you might ask when you see this construction is, this condition of algebra being generated in degree 1 is really unfortunate. It's kind of it's annoying, and so the first generalization of the whole thing is the answer to this question of how to get rid of this condition of algebra being generated in degree 1. Maybe. So first generalization. Also, I promised to talk about infinite dimensional vector space example, and I kind of missed this. But in the case of toric varieties, in the case of spherical varieties, actually, there is this intersection theory which takes into account all possible equivariant compactification of your homogeneous space. This is called ring of conditions, which was defined by De Concini and Procesi. And just by construction, it's very infinite because you can have any possible equivariant compactification. So in the case of toric varieties, it's somehow more tractable. So it tells you that you need to take all possible toric, the limit of Chow rings of all possible toric varieties under the subdivisions of your fan. And the conveniently, the construction like this, it behaves very well under such limits. So the ring of conditions, it's maybe now a corollary. Ring of conditions of C star to the n is given by ring of differential operators on the space of all polytopes, which we don't specify the normal fan now, all virtual polytopes, modeled out by the annihilator of the volume polynomial. So, yeah.
Can you say again, what precisely do you mean by diff P or diff P signal?
In the infinite dimensional.
Either case.
In every case, in finite dimensional vector case, if you choose your basis, you can just take polynomial ring and partial derivatives. But really, what it is
In what? In the normal vector.
in the normal, yeah. But really, if you have a vector in your vector space, you have a directional derivative, and then you can take the ring which is generated by these operators.
But what is the vector space? That's what.
Vector space. What is it?
Yeah, that's.
What is vector space? Yeah, sorry. So I do have. Okay, that was it. So if I consider all possible polytopes, they form a semigroup under the addition, and so they actually form a semi-vector space because I can also scale. So what I can do, I can take the Grothendieck group, which corresponds to this semigroup. So this is maybe the easiest way to define this. But as I said, they really correspond to certain geometric objects, which you can realize as a linear combination of convex polytopes. And not any linear combination of convex polytopes will be a virtual polytope, but they do have geometric interpretation, not just like the abstract group completion definition. But the easiest way to define them is maybe via considering the Grothendieck group of the polytopes under Minkowski condition. Yes.
How does it compare with just the group of T-stable divisors?
So again, a group of, right. So these guys will be, so the group of T-stable divisors will be, it depends what you mean by this. If you look at after we are taking rational equivalence, then it will be a quotient of this. So basically the way to determine such a polytope here, it's enough to know the support numbers, and the support numbers will be the coefficients of T-stable divisors. Yeah, exactly. Any other questions? Yeah, and here I just do the same, but without fixing the normal fan. I just take in all of them.
But in this first case, I can just take R to the number of rays.
Yes. Yeah, this first one is a finite dimensional vector space with a basis given by the rays.
Right, then how is it a quotient of the? I thought you said earlier that.
But this is a vector space itself. But now I take I take this ring of differential operators of this vector space. So you can think about this as a symmetric algebra generated with this vector space.
I thought you were saying the group of T-stable divisors was a quotient of this, but that would be the same as the number of rays.
Oh, well, what I was saying is, okay, yeah, I guess. So what I was saying is that T-stable divisors can be linearly equivalent to each other. So if you take a Picard group, then Picard group will be a quotient of.
So this is just the group of.
This is yes, yeah, that's what I meant. Okay. So going back to the first generalization, and this really takes care of this degree 1 condition. Maybe let me start with a construction. And maybe again, I probably will not. Okay. So construction is very similar. We start again with vector space V. And with some polynomial f on V. But now this polynomial is not any more homogeneous, but we ask it to be weighted homogeneous. So what this means is that one way to say it is like if we write this polynomial if we choose a basis and we write this polynomial in this basis, then we want each basis vector to have certain weight, and the sum of the degrees of monomials counting with these weights should be the same for every monomial. So in our way, we can say that there is a scaling action on this vector space V by R plus, and this polynomial is invariant under this action. So if we have just the usual scaling action, we just scale every vector by R to get usual homogeneous, but we can scale different parts of a vector space with different degrees, and this will add weighted parts. And then we can do the same thing. We can associate this algebra by taking these operators on vector space V and quotienting it by the annihilator of F. And then the statement that this algebra now satisfies everything, but just by construction, we allowed different elements have different degrees. And so this algebra is graded and has Poincare duality. And moreover, this construction is universal in exactly the same way. If you have now any graded algebra with Poincare duality, you can construct it in this way. Maybe this is the first theorem.
So graded, do you mean weighted graded? Yeah, or what do you mean by graded?
So this is an algebra, and the way it will be.
Oh, is it just not generated degree one? Sorry.
Yes. Maybe I'll tell it. Maybe it will be clear. So this is the first maybe theorem. Is that if you have any algebra A, which is graded and satisfies Poincare duality, can be constructed in this way. And and again, let me tell you explicitly what this vector space and what this polynomial is. So for vector space, we need to take any vector space with a map to the algebra A, such that the image generates A as an algebra. And so as a polynomial f defined on V, the way it works is the following. So we want to define a polynomial which in the vector space. So we use our map here to embed it into the algebra. And then on the algebra, what we do is the map, we have a map to R. And the way it works is we take an element x here and we map it to the degree of the exponentiation of exponential power series of x. So if we have an element in algebra, then what we can do, we can take its formal power series in this element. And what we can do then, we can take the degree of each component. So some components, most of components will disappear because they will be of the wrong degree. But some of them will survive, and then this will define a polynomial on, this defines a polynomial in algebra A. and in particular defines a polynomial on V. And so the theorem says that if you do this, then your algebra A is isomorphic to the algebra AF, which comes from this pair V and F.
What does degree mean? Just take the,
Degree means just it's like
Just look at
that's the
the-
degree
Ah.
D component. Yes, degree is we take isomorphism of D component, D dimensional component with the field, and the lowers they just go to 0. And so the way I wrote it, actually, this F might not be a polynomial. It depends on how you map your vector space V into your algebra. But if you choose some homogeneous generators of algebra A, and if you take your vector space V to be spanned by these homogeneous elements, then this F will be quasi-homogeneous polynomial, or weighted homogeneous polynomial in exactly the same way. So somehow the extension is very similar to what it was in the generator in degree 1. And maybe just like one more comment, like if we have algebra which is generated in degree 1, well, then we can again take this map V, which just maps it to degree 1 component, and then among all of this exponential power series, only x to the n component will survive, and this recovers the usual degree 1 construction. Are there any? So maybe again, just to give you one example where you can use this to talk about some cohomology rings or Chow rings is something which is called Toric variety bundles. And again, yeah, let me not really define them, but let me tell you. So these are certain class of fibrations, of locally trivial fibrations, which have a toric variety as a fiber. And these are fibrations over some base B. And you can consider them algebraically, you can consider them in smooth category, and just as like a very different, slightly different constructions. But let me give you one particular example of how to use this theorem to give to compute at least some part of their cohomology rings. And the way it works is as follows. So any such bundle, so the only thing which we need to know about them is that first of all, that any cohomology class on this Y sigma is either from the base, is either a pullback, so maybe let's call this back P, is either a pullback of some class from the base or toric class. Well, of course, you can combine. You can take a toric class and multiply it by something which you pull back from the base. So by toric class, I mean the toric variety has this orbits, and in these orbits they have some cohomology classes. Turns out that there is for each orbit of original toric variety, you can extend this orbit to get some subvariety of the whole toric variety bundle, and this defines you some class in cohomology. So in particular, if you think about this, so your cohomology ring of the base can be quite arbitrary, but the new things which you added, these are toric divisors.
Are the toric classes unique, or are they just like closing up some kind of?
For each orbit, there is a unique subvariety here, so it's well defined. Yeah. So in particular, like there are exactly number of raised many toric invariant divisors in here. So it turns out actually toric has a fiber-wise section. This is part of it.
When we talk about algebras, like in that context,
Yes.
are we talking about commutative algebras?
Yes, commutative.
So here B, for example, cannot be
Yeah.
something like C star.
That's why. Sorry. Yeah. No. Yeah. That's why I'll only recover even part of cohomology.
Okay.
Using this map, using this
Let's
method.
look at the even parts.
Yes, yeah, that's, yeah.
But if Y was even like a projective bundle, what would the toric classes be there? Because I don't, you
Right, because it's a special class of vibration. So these are the ones which still have equivariant structure on the fiber, and a general projective bundle will not have T action of the full torus action on the fiber. So it's not any vibration of this sort. This is really special subclass. But maybe let me say this subclass include something which is called horospherical, toroidal, horospherical varieties. And yeah, so maybe this is the main motivational subclass of toric variety bundles. And the second piece of information which we need to know is that, again, this for any such vibration of this sort, we have a map delta from the character lattice of my torus T to the Picard group of the base over to the, really I only will need to map to second cohomology of B. So really the map is defined to the, it defines it for any character complex line bundle on the base B, but we can take its first Chern class to get a cohomology second. So as I already mentioned, now I will switch to even degree cohomology. So of Y sigma. So this will be my, actually, I'll just say that this is my AI. Under certain condition, I can also, if I know that my base B is nice, so the Chow ring satisfies Poincare duality, I can also do the same calculation for Poincare duality of the toric variety bundles. But in general, of course, Chow ring does not satisfy this. So if I want general base, I can do maybe even cohomology instead, if we have everything smooth and complete. And let me fix some generating set for the even cohomology of the base and some polynomial f, which gives me even cohomology part of the base. So let me fix some pair B and F, such that if I construct this algebra AF, I will get my even cohomology part of the base B. So this is something I want to have. So then theorem, which is, again, it's a theorem with Khovanskii, but it's based on some previous work with Johannes Hofshire. It's called, and myself, which tells you if we know this generating polynomial for the base, we can also reproduce the generating polynomial for the whole total space of this vibration. So then the polynomial F defining cohomology ring, even cohomology ring of this total space of this vibration is given by so as I said, we have these classes, all the classes, they come either from the base or from toric devices. So really, to generate the cohomology ring of this total space, we need to add to the generating set of cohomology class, the cohomology ring of the base, only toric divisors. So this polynomial F will be defined on this vector space V plus P sigma. This is the vector space of toric invariant divisors. And if I want to evaluate F at some pair, gamma delta, well, this will be the integral over our polytope delta of F of gamma plus of some expression which only depends on the homomorphism. Oh, sorry, delta. On homomorphism delta and intersection theory of the base. So what is written here, we have our toric variety bundles, they come from this map, from character lattice to the second cohomology. So we can evaluate this generating polynomial for the base in this sum, and what we get is some polynomial on the character lattice of our torus, and what we need to do is to integrate this polynomial over the polytop delta, and that gives some intersection numbers of the total space. So again, as a corollary, you can obtain the description. So this polynomial is not anymore homogeneous because it has different degree components of this class which come from the base. But using this description and construction of duality algebras, you get a description of even part of cohomology ring of the toric variety bundles. Yes. So maybe let me move on to a different way how you can generalize this construction, the original construction, and this will be motivated. So the first generalization was just motivated to more general Chow rings, to give some description for more general Chow rings, so for Duality algebras. But this second generalization is motivated by computing some other cohomology theories. And the particular one I have in mind is Grothendieck group. So second generalization. And this is motivated by computing K0 of some varieties for the Grothendieck group, Grothendieck rings of this variety. So the second generalization is very similar to the first. Is very similar, but what it does, it replaces the continuous version with its discrete analog. So maybe again, let me start with algebraic construction. So in algebraic construction starts with some starts with some lattice lambda, which we assume it's some lattice. So it's a free abelian group. And again, it can be finitely generated or infinitely generated, so this is not so important for the construction. And we can start with some function, actually, g on this lattice. And if we have a lattice and the function on it, well, then we can define, so a pair defines lambda g, defines an algebra. So here my algebra, I start on the vector space. I have natural operators which act on functions are differential operators. On the lattice, I have a similar discrete version, which is called shift operators or difference operators. So I can take this algebra of shift operators on this lattice lambda, and I can quotient it out by again those operators which completely annihilate my function g. Turns out that any algebra which you can construct in this way satisfies some nice duality properties, which are, so this algebra not necessarily graded anymore, but nevertheless it satisfies certain duality properties, which, for example, is these duality properties are satisfied by rotating ring of smooth, complete toric varieties.
So is the shift operators isomorphic to like sim of the lattice?
No, they isomorphic to, yeah, maybe let me say this. So they are isomorphic to group algebra of the lattice. So the shift operators, again, if I choose my, let's say, basis, my lattice, then here I have, this will be group algebra on this, this will be ring of Laurent polynomials in this variables ti's. And each of the ti is the way it acts on a polynomial, or like on a function g, is what it does, it shifts the argument of this function by the ith basis vector of the lattice. So this is g of x plus ei. This is basis vector. And of course, I have ti's, but I can also subtract, and this gives me a round polynomial ring. And if you want coordinate-free weights, will be group algebra of this lattice. Yes. And of course, so that's how we act. And then we have linear combinations of these operators, and we want such linear combination which completely annihilate our function of the lattice. And that's the ideal with quotients in line.
Shift operator operates on polynomials or what kind of functions?
Yes, we can restrict. Okay, I'm saying like any function, and what everything I will say will be true, but somehow if you take random function, this quotient will be not very interesting because your ideal will be actually trivial. So the interesting quotients, they really come from polynomial functions, because if you have a polynomial function on finite rank lattice, then the quotient will be Artinian, it will be finite dimensional. Or you can allow yourself quasi-polynomial. Like, I mean, to get something interesting, you need to restrict your class of functions. Yeah, for example, if you apply shift operators to polynomial, you get a polynomial. So polynomials is a module under this action. Yeah. So the duality property which algebras always have is something which we call Gorenstein duality. And this is
and the choice of R here is like arbitrary.
yes. I will maybe comment on this. Yeah.
Can I do it like put Z?
Yes, you can. Yeah. Yeah, you can. Yeah. You can put Z, and you can also put maybe like equivariant Laurent polynomials if you wish as a coefficients, and then you get some description of equivariant K theory, etc. So this is also possible. Yes.
Yeah, sorry, could you just clarify again how you in the theorem combine gamma and delta of lambda to evaluate it?
Sorry, yeah, so delta is a polytope which lives in the character lattice of my torus. So delta is a map from character lattice to the second degree cohomology. So what is written here belongs to H star of the base.
Oh, I thought that f was a function on V.
Yeah, you're right. Okay, let me replace this V. I can take any generating subset. So let me replace this V with the full cohomology. Sorry, with
V with A.
With A star of. You can do. I mean, you can do. It's a little bit overkill, but yeah. Sorry. Is it? Okay, so coming back here. Yes. So any algebra which obtained as these quotients, they satisfy something which is called Gorenstein duality, and this is the following thing. So let A be a commutative algebra. And let L be some linear function on A. So then we can define as inner product on this algebra A using this linear function L. So the inner product between two elements, A and B, will be just the relation of this linear function on their product. So since our function L was linear, this will be bilinear pairing, and since algebra is commutative, it will be symmetric. And and we say that A satisfies Gorenstein duality. If this product is non-degenerate. So the one example of this would be the Poincare duality. Then your function L will be just a degree function on your top graded component, and then of course like this pairing will define you non-degenerate pairing, which we have in Poincare duality. But this is a version of duality which is well defined for non-necessarily graded algebras. Reason we call it Gorenstein is because if your algebra A was Artinian, existence of such pairing is equivalent to Gorenstein property of the algebra. So in slightly different contexts, such pairings also called Frobenius pairings, but I guess this usually happens when algebra A is non-commutative, but you can still talk about similar construction. And again, one class of algebras which satisfy such duality, apart from Poincare duality algebras, are K-theories of smooth toric varieties. So for K-theory, so for smooth complete toric variety, we can consider its K0, which is a Grothendieck group of vector bundles, so like sigma, and such a group satisfies Gorenstein duality. With respect to this linear function, which is the earlier characteristic of the vector. So in other words, you can define the earlier pairing between two vector bundles. And by definition, the earlier pairing between two vector bundles is the earlier characteristic of the tensor product of these vector bundles, of this vector bundles. And this pairing is non-degenerate if we work on smooth complete toric varieties.
Is this Lamarck's theorem?
I guess it is. No, there is like actual theorem, like much more general about all cohomology theories when they satisfy duality with respect to push forward to the point. And there is a statement that if you have a cellular decomposition, like if you have a paving by affines, I guess for it, like this particular statement is like it's more easier result.
This is also a function of Prisbacher and Rock plus Poincare duality.
Exactly, yeah. You can deduce it like this, yeah.
With Q coefficients.
With Q.
Yeah, but what's asserted here is stronger.
I think you can like use this and then find a class so its pairs non-trivially after you apply sharing character map. And that will give you, by removing off, that will give you all characteristic computation which is non-trivial somehow. I think this statement you can deduce.
That it's unimodular.
Yeah.
Not long.
What do you mean by non-degenerate? You mean like unimodular? But that is what we're seeing.
Yeah. Right. Okay, so maybe, I really out of time, but let me formulate last last theorem and application. So the theorem, which is going with Evgeny Smirnov, will tell us that this construction, which I discussed here, is universal in some sense. So any algebra A which satisfies Gorenstein duality and generated by invertible elements comes from this algebra from the construction, from discrete construction. And so the corollary of this is that you can give a description of rotating group of toric variety by using this language. So for a smooth complete x sigma, we get that k0 of x sigma. So if we want with real coefficients, so we need to tend to it with r, is isomorphic to the ring of shift operators on the École, on this space of virtual polytopes, but with integer coefficients modeled by the annihilator of the earlier characteristic of shifts, which turns out in toric geometry can be computed as a number of lattice points instead of a polytope. We get a hard polynomial. So there is this description for smooth complete toric varieties, but there is this very similar description also for full flag varieties, and again, more generally for everything. For any spherical varieties, which is with cohomology generated in degree 1, with Chow ring generated in degree 1. Okay, so maybe a couple more things, but let me stop here.
Questions?
Is this a lambda ring or just like a general polynomial G?
Yeah, so this I don't know yet, but that's some questions which I would like to think about. And also there are two constructions, and you can start with a vector space which is spanned by a lattice, and you can have like two polynomials, you get like this A and K. So what's the condition, what's the relation between these two? So there is a version of Riemann-Roch statement which Chern characterizes isomorphism between these two, and which pairs of polynomials you get as isomorphism. So statements of this sort, and this lambda ring is something which I didn't investigate, but yeah, it's something I would like to understand.
There are some similar statements in quantum versions, like quantum cohomology and quantum K-theory. They are both relations. So the relations are given by some annihilators of some J function of the theory.
Right.
They have to start with some differential or difference operators. You see what annihilates the J function, and then you transform that into a relation. Is there anything? Is there any connection?
Probably is. I don't know quantum theory well enough, but usually the quantum rings there are some deformations of usual.
Sure, you have to add. So I think you're
and it probably what you get is like your J function would be something like.
No, that's the usual pairing, but the J function is the analog of.
The J function will be yes, but taking into account like this deformation variables. Probably this is similar. But I don't know quantum cohomology well enough to make this precise.
Further questions? No, let's thank the Leonid.